Hi, welcome to video 3.4b. This is the second video in the series on intermolecular forces. We are going to focus this video on molecular polarity. And just so you know, by the end of this video, you should be able to use VSEPR theory and molecular geometry to make predictions about the polarity of molecules. Now, let's start off just reminding ourselves what bond polarity is. This was the subject of the previous video, and if you need more details, feel free to go back and watch it. But remember, bond polarity comes about because there's a difference in electronegativity. So sulfur and fluorine here have a difference in electronegativity, so that makes this bond between the two polar. But when we're talking about molecules, now we're talking about a group of bonds that exist between a whole group of atoms. So here we have to consider more than just the single sulfur-fluorine bond. Here we have to consider 1, 2, 3, 4, 5, 6, and their arrangement in three-dimensional space to determine whether that whole molecule is polar. Now, there are two qualities, as my clock ding-dongs, that a molecule must have in order for it to be polar. A molecule must have polar bonds, and it must be asymmetrical. So I think it's important for us to review what polarity actually is. Remember that polarity is an uneven distribution of the electrons around in a molecule. So in this case, here we have HCl. HCl has a single bond. It is a molecule, so this is kind of the simplest case. In this case, remember, hydrogen and chlorine are sharing those two electrons, and those two electrons are moving back and forth and all around. Now, because chlorine is more electronegative than hydrogen, those electrons are unevenly distributed around the two atoms in that bond, and they are found more around chlorine than they are around hydrogen. They are found more around chlorine because chlorine is more electronegative. Chlorine's electronegativity is 3.0. Hydrogen's electronegativity is 2.2. So we know that that's a polar bond, and we should also be able to determine that this side is the negative, more electronegative, so that makes that side the negative side and this side the positive. And what we know is that when we have two different sides to something, that makes it polar. Like the North Pole and the South Pole, two different sides of the Earth, that makes the Earth polar. A North Pole of a magnet, the South Pole of a magnet, that makes a magnet polar. Well, a molecule is no different. There are two sides to a molecule. This molecule, HCl, is polar because there's a negative side to the molecule and a positive side to the molecule. Now, if we make the molecule a little more complex, like this molecule down here, this is water molecule. Well, is it polar? And the answer is yes, it is polar, because if we look at it, there is, I'm going to split it right in half, right down the middle. We'll notice that this side of the molecule, where this electronegativity of these atoms is 2.2, is more positive than this side of the atom, where the electronegativity is 3.5. That makes this molecule polar. So the electrons here that are being shared between the hydrogen and the oxygen, that means that the electrons are going to be found more around the oxygen than they are going to be found around the hydrogen. So that means the oxygen is the negative side of this. This is the negative pole. Okay? So let's look at the specific factors that affect molecular polarity. Okay? Bond polarity affects molecular polarity. How does that do that? Well, the only way that a molecule can be polar is if we start off with the bonds being polar. If you have non-polar bonds, then you cannot have a polar molecule. So if we look here, hydrogen has a electronegativity of 2.2, Carbon's electronegativity is 2.5. The difference is here is 0.3. That is a nonpolar bond. Any of these bonds are nonpolar. So that means that the electrons, because that's a nonpolar bond, that means the electrons are being shared equally between the atoms in the bond. Therefore, there's no unequal distribution of the electrons throughout the molecule. Okay, now the next example that we have here is carbon tetrachloride. So if we look here, the electronegativity of chlorine is 3.0 and carbon is 2.5. And so the difference between the electronegativity there is 0.5. Now 0.5 is polar. So what that means is that the molecule has a chance of being polar. Now, it has a chance of being polar because now we have to take into account something even in more detail, and that's going to be the symmetry of the molecule. So what I'm going to do is I'm going to take this, I'm going to move these up here, and then I'm going to take this guy down here, and I'm going to look at this. So now symmetry of the molecule, actually I'm going to put this up here, put this here. The symmetry of the molecule affects polarity as well. So now if we take a look here, I'm actually going to show the molecule. So we have the shape of the molecule right here. This is carbon tetrachloride. Now that molecule right here, this is the shape of that. Now yes, the bonds are polar, but if we look at it and manipulate it, no matter how we do anything with this molecule, the molecule is completely symmetric. The fact that that molecule is completely symmetric, no matter how we manipulate it, that means that there's no way that the electrons can be unequally distributed throughout the molecule. So that means that that molecule, even though it has polar bonds, is a nonpolar NP molecule, nonpolar molecule. Now let's take a look at SF4 here, sulfur tetrafluoride. Now this has polar bonds, 1, 2, 3, 4. Those bonds are polar. But this shape is seesaw. That's my favorite shape. So let's take a look at what this looks like. Now if we look at this guy is seesaw. So seesaw, yeah, has some symmetry, but if we look at it down from the axial bonds here, you'll see that it is not completely symmetric. It doesn't have 100% symmetry like the tetrahedron does. And so this molecule is polar because it is has both polar bonds and has an asymmetric shape. So that's one way that symmetry affects the polarity. Now, another way that symmetry affects polarity is if we have something like this molecule. Okay, this is trichloromethane or chloroform. Now, this molecule also has polar bonds. Okay, so let's see, this bond, and this bond are polar, so we have 3 polar bonds, and then we have a non-polar one over here, which I will highlight in red, I guess. So that's non-polar. So here's the thing, polar bonds, but this guy was a tetrahedron up here, carbon tetrachloride was a tetrahedron up here, so don't you think that should have, this guy maybe should be polar? Well, no, because what happens is this guy here has an unequal distribution of electrons. Because if you look, can't you see that all the chlorines there are on one side of the molecule? All the white atoms, do you see the white atoms there? They're on one side of the molecule. Well, that means that there's an unequal distribution of chlorines, or of electrons around the chlorines. So that makes this guy polar. Okay, you can see that he is not symmetric completely, as opposed to maybe something like This guy, because all 4 atoms are the same, no matter what we did with this guy, he was going to be nonpolar. This guy is polar. The one with the green atom, this guy. So you can see, okay? So what we can say is there could be asymmetric exterior atoms. So it could be either the asymmetric shape or asymmetric exterior atoms. Okay, well, let's try it yourself. Let me turn off the camera here. And now you can see the rest of the electronegativity table there. And so why don't you hit pause and answer the question, are the molecules polar? If so, indicate where the partial charges are on these molecules. Okay, so I assume you paused the video. Let's take a look. Okay, well, this guy here is non-polar. Yes, the bonds are polar, but it's got a symmetric shape. Octahedral is symmetric. Okay, so now I'm going to take the next easiest one, and that's this one here, sulfur dioxide. Sulfur dioxide is polar. A bent shape is polar, but now I'm saying where is the partial charges? Well, the oxygens are more electronegative than the sulfur. So that makes this side the negative side. Oxygen's 3.5 and sulfur 2.6, so that means this is partial positive. Now the last one here in the middle, bromodichloromethane, this one is going to be pretty difficult, but we can still figure it out based on unequal distribution of electrons and electronegativity. Which one is more electronegative, chlorine or bromine? Well, chlorine is more electronegative. So this is a polar molecule because it has asymmetric exterior atoms. And the fact that the chlorine is the more electronegative atom makes this partially negative. And then this side of the atom is partially positive. So we can determine the polarity of the molecule based on electronegativity differences, and we can base it on symmetry and Vesper theory and all those wonderful things. Okay.